Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. All right. Yeah. Alhamdulillah. So, because you're in one room, so the others can hear my voice through your device. All right. So let's start our discussion for today before you have a long vacation. So before we continue our discussion, let's begin with praying together. Allahumma inna nas'aluka ilman nafi'an wa rizqan thayyiban wa amalan mutaqabbalan. Allahumma inna na'udzubika min ilmin la yanfa' wa min qalbin la yakhsha' wa min nafsin la tashba' wa min da'watin la yustajabu laha. Rabbana zidna ilma warzuqna fahma. Allahumma la sahla illa ma ja'altahu sahla wa anta taj'alul hazna idza syi'ta sahla. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Okay, then you can call them because you already solve all the problem, so even you can miss some of the discussion. Okay, please call them. All right, so let's continue the discussion about number theory, and let's finish let's finish this in this lesson, in this session. So in the past meeting we have discussed until problem Q, and I have show you the implementation about that. Okay, yes, I think some of the of my solution is false. Even in problem Q, I tell you wrong solution here. Okay, that's it. So in the past meeting, I told you about this trick, but after I checking, this trick is not correct. So that's why in the sample input, the solution gives the wrong output in the for test case. So why this is incorrect? Because actually we want to plot the division for each term, not the total. So you know, when I show you a formula like this, n minus n divide e minus n divide q plus n divide pq. All right, but all of them should be rounded down. And in the past meeting, I told you that the formula is same as like this. But in fact, this is not always same. Why? Because we need to round down one by one, not both of them divided by q and then rounded down. So this trick is incorrect. And one of the case is the fourth case in the sample input. All right, that's why we cannot do this, but we should compute all of them one by one. But don't worry, the number of prime here is so small, so it is not hard to make the complexity 2 to the power of the number of prime. All right. Okay. For example, like this. So let's create a vector, for example, a vector z, and then z dot pushback m divided by y, and then here we don't use this formula, but we will do like this. We will iterate all values in z, and then push back minus zi divided by the prime number. All right. And finally, we will return the sum of z. So just iterate for all value in z. And then plus I. Okay. So the correct solution is like this. But let's check whether the output is correct or not. Okay, floating point exception. I think the floating point exception may be here. Okay, we should not use I here. So let's use J. All right, and finally the output is correct. Okay, and how about the other problem? Problem M, I think. Okay, in problem M, we will factorize A and B, and let's check for its prime number. If there is a prime number with power x and y, just make sure that x or 2x is greater than or equal to y. At first, let's assume x is less than y. If x is greater than y, then just swap it. Then just check whether 2x greater than or equal to y or not. And then if this is valid, so okay. We also need to check whether x plus y divided by 3 or not. Yes, yes, of course. We can check both of them. We can check both of them. This trick is also correct. Or we can assume x less than y by swapping it. So if x greater than y, just swap x and y. Okay, all right, that's great. So please join the Zoom. But time limit exceeded. All right. Okay, I think n is so big. Yes, if we do that, so the complexity n times square root a. So how to optimize it? Maybe we can check, is a times b is a cube number. Okay. Do you know how to check whether this value is cube number or not in O1 or O log n? Log n is still accepted. Yes, that's it. Using binary search. Just binary search and just check whether mid to the power of 3 is equal to this or not. If less then we can check to the right, and then if greater, then we can move to the left. And yes, we can also using a function, so the complexity can just O1. Just check what is a times b to the power of, okay, or root 3, and then just check, just round it, and then just check what is that value to the power of 3. Is it equal to a times b or not? Okay, after that, what shall we do? Just make sure that both of them is divided by this. Is it correct? If both of them is divided by this, it is must be correct. The solution is like that, I think. Okay, so no need to factorize a and b, but just check. Let's define c equal to a times b root 3, and then just check whether c to the power of 3, maybe you can round it or truncate it. C to the power of 3 equal to a times b or not, and then is c divide, sorry, c can divide b, c can divide a and b. If both of the condition is correct, then just see out this, else see out no. All right, so the complexity is just O1 or log n if we want to use binary search. All right, okay, so just try that. Okay, after that, how about the other problem? Solution in B. Yes, my solution in this is still time limit exceeded. The complexity is same as SIF, but can be optimized it, okay? The worst case is where when b equal to 1. So we can check whether c is prime or not. Probability of this is only O max A, OA, and then we just iterate this when C is prime. I think the complexity is just like C. That how this solution time limit exceeded. Participants already output this, but time limit exceeded. What does it mean? We can use the other language. All right, good idea. Which language you prefer? Yes, I think 23 is not stable yet. And sometimes more native, more faster. Okay, the solution is here. Okay, that's it. So sometimes we need to change the language or just use the most stable one. Right, and then let's continue to the next problem, which is problem R. Or can we discuss it from the last? So let's discuss from the last problem, which is problem Z. So in problem Z, okay, alhamdulillah. Thank you very much. So with the same solution but using different language. And the time is almost 1 second. All right, let's move. So for the last problem, given a tree consists of n vertices, and then all vertex is weighted. So the weight is on the vertex, not on the edge. So there's a value on its nodes, and then we want to find the maximum distance, or let's say we want to find the valid pair that the distance is maximum. Valid pairs means the greatest common divisor in the path between x and y is greater than 1. Alright. And among all the valid pairs, we want to find the maximum one. Alright. And for example, given 3 nodes, one connect with 2, 2 connect with 3, the value is 2, 3, 4. So if we use this, the greatest common divisor is 1. So this invalid pair. Here is also invalid pair. And this one is also invalid pair. But 1, 1 is valid pair. But the distance is only 1. You know, the definition of distance in this problem is the number of vertices, the number of nodes, not edges. So the distance between 1 and 1 is 1. That's why the output is 1. But what if the graph is like this? Then the maximum distance of valid pair is here, not 1 with not 3. The distance is 2, and the greatest common divisor between them is 2, not 1. Alright. And how about this? Any pair of nodes, the greatest common divisor is 1. That's why the output is 0. Alright. So at first, do you know when the output is 0? It is quite obvious. In what case the output is 0? When all are same? Not really. What if all of them the value is 2? Then what is the answer? Then the answer is 3. Is it correct? Because greatest common divisor of them. Yes. All are has value 1. All same and 1. Alright. Okay. Then how to solve this? Actually, we want to use brute force for our prime numbers. So the greatest common divisor greater than 1 means both of the value in the path can be divided by some prime number. For example, if both of them can be divided by 2, then the greatest common divisor will be multiple of 2 and never become 1. Okay. And also if both of them can be divided by 3, then the greatest common divisor also multiply of 3. And also the other prime numbers. How about 4? Okay, if both of them is multiply of 4, then the greatest common divisor also multiply of 4. But you know, if 4 is valid, then 2 is always valid. Okay, so no need to check 4. We can just use 2. Okay. Yes, of course. Let me discuss the problem one by one faster. Okay. So because we only need to check for all prime number. So just iterate all nodes that the value is multiply of that nodes, multiply of that prime number. After that, just check what is the maximum distance, or it it means the diameter of every component. That's correct. Okay. And what is the complexity? So the complexity is equal to On for its prime in the worst case. But for its node is only computed in some prime numbers, and because a no more than 200,000, then the number of prime number can divide a only a little. Let's check until which prime number. Okay, I think until 13, only until 13. Because if we multiply until 17, then the value is greater than 200,000. That's why the number of prime is only 6. Yes, that's correct. At most 6 primes. So the total complexity is 6n, or we can just write it on. Okay, so it is so fast, even we use brute force. All right. After that, let's move to problem Y. So for this problem, it is a query and update problem. The query is quite simple. So given an array with size n, and then we want to do m query with query with 2 types. One of them is update, one of them is query. The query is so simple. We just need to find the sum from L to R. And then the update is we want to replace for L to R from A become GA. What is G? G is the number of positive divisors. All right. Then how to do this faster? Actually, we can still do this one by one. Why? Because the number of operation we need to do is so small. Even the initial A is a million, but if we want to change into GA, then the value become 49, isn't it? What is the number of divisor for a million? This is equal to 2 times 10 to the power of 6. Yes, approximate cube. Okay, so small. 7 times 7, 40. Yes. Okay, but we want to add by 1 for each power. So the number of factor or the number of divisors is 49. And then if we do it again twice, so from 49 become only 3. Yes. Yes, because 7 to the power of 2 become 3. After that, if we do it 3 times, from 3 become 2. Okay. Then from 2 become always 2. Okay. So after reach number 2, then we should do nothing. Okay. And also for 1. For 2 and 1, both of them are the best case. So after reach this value, then just do nothing. All right. So actually the number of operation is so small, even for maximum A, number of operation only 3 times. But maybe the other value can be more than 3 times, but still small. All right. After that, what shall we do to optimize the complexity? So in order to optimize the complexity, when we do replace, please just update for a value that is still greater than or equal to 3. Okay. Yes, at most 10 times. So small, right? Less than log. Less than log. Okay. That's why we can use brute force. But please avoid to update a value that is less than 3. Because if we update all of the value, including the value less than 3, then the complexity is n squared. But if we ignore the value less than 3, then each index only updated at most around 10 times. That's why the complexity is around 10n. Okay. And then since there are some update, but the update is point update, and also the query is only sum, we can use Fenwick tree. We can use segment tree as well, but of course, complexity is, or the implementation is more complicated. Okay, so using Fenwick tree is more simple. Fenwick is simple. All right. Then how to check just a value that is greater than or equal to true, equal to 3? Then we can do using some data structure. Maybe we can use set, or even we can use disjoint set union. If we use set, at first just insert all of the index, but if some index is reached 2 or 1, then just erase it from the index. After that, every time we want to replace, just do lower bound until index L, and then just iterate 1 by 1 until R. Okay, that is if we use set. If we use this disjoint set union, then at first just create a node and all of them pointing itself as its parent. But if one of the value reaches 2 or 1, then just point the next. All right. So the leader of each node is the first value that greater than or equal to 3. So from this, just find the leader, and finally we jump to this, and then just go to the next, and then jump to the leader, and go to the next value, and go to the next, and jump to the leader, and so on. Okay, sometimes go to the leader is itself, and so on. All right, until R. So the complexity is O 10n plus m log n. Okay. Is there any question for this problem? So just continue to the previous problem, which is problem X. For this problem, there is a sequence of n positive integers, and the prefix for all prefix sum in this sequence is a perfect square. For example, there is a sequence like this, then the perfect sum is like this: 4, 9, 25, then 36, and then 100, 145. Both of them are all of them are perfect square. Okay, but unfortunately, we don't know the whole sequence, but we only know the even index. We are only given the even index, so we only know 5, 11, and 44, but we don't know the odd index. So how to restore this in order to make the the perfect sum is perfect square. All right. Then at first, in order to make all of them is perfect square, we need to make that all of the sum from this to this is perfect square, and then from this to this it's perfect square, and so on. So at first, we need to find two perfect square that the difference is 44. Is it correct? And greater square number is better. If the smaller number cannot achieve the correct sequence, then sometimes the greater value can achieve the correct sequence, and vice versa. If greater value, greater square cannot achieve the correct sequence, then the smaller one, of course, cannot achieve the correct sequence. Okay, so just find the greatest perfect square, that if we reduce it by 44, this value is also perfect square. Okay, so just find the maximum A that satisfy this. Okay, and you know A squared minus B squared is A minus B times A plus B. So in order to make a maximum, so we want to maximize A plus B. It means we want to minimize A minus B. So just find the minimum value that is valid for this value. So just check for its value here. And you know, if A minus B is even, then A plus B will be even as well. If A minus B is odd, then A plus B should be odd as well. That's why if 44 is even, then just make it 2. The smallest even number. So A plus B is 22. Okay. So just use a simple linear equation. We will know that A is 22 plus 2 divided by 2. This is equal to, yes, that's it, 10 and 12. So we know that here is 12 squared and here is 10 squared. After that, just find the other A and B. That is the difference is 11. But please, A should be less than 10. Why? Because all of the value in the sequence is positive integer, so cannot be 0. And every square number less than that is accepted. For example, 9 squared, then just make it the difference between these. If this is 8, just make it different between this and so on. So just choose any value of A as long as it is less than 10. All right. What does it mean? It means we want to find A minus B times A plus B equal to 11. But A should not greater than or equal to 10. A should be less than 10. So again, we can just check for our divisor or factor, for example, 11, 1, and 11. And if we use this, finally, the value of A is only 6, and 6 is less than 10. All right. So it is correct. Then just continue using the same way from the other values. All right. And sometimes there is no valid A and B because there is a constraint like this. Okay. For example, for the case A squared minus B squared is 45, just like the previous one. If A should not greater than 12 or 11, then there is no solution. Because if we use 1 and 44, then one of them odd, one of them even cannot be used. If 2 and 22, then A is 12, more than 11. If we use 4 and 11, then one of them is even, one of them is odd. So we cannot use anything. So in that case, just output no. Okay. All right. Is there any question for this idea? After that, after we know the solution, then what is the complexity for this? Let's see. From the constraint, x is only up to 200,000. So of course the number of divisor, if you want to find out the divisor, the complexity is square root of this. Okay. Or even we can use brute force. That's it. Maybe Abdullah use brute force as well. And I also use brute force when I solve this. How to do that? At first, we have to see this for the last value. For the last value, if the distance is at most like this, then the maximum perfect square is only around this value as well. So how to achieve the distance is equal to this, a minus b equal to a plus b. Then a minus b can be 1 and a plus b can be this value. So a is only 100,000, right? So the last value in prefix sum is 100,000 squared. Okay. So we can just brute force one by one. So instead of we factorize that, we can just brute force. Can we use 99999 as the previous value or previous prefix sum, and then can we use 99998 as the previous prefix sum, and so on. We can just brute force it. So we just need to check 100,000 times. And then how to check it? How to check whether this value is correct? So this is A. We want to check whether this A is valid or not. So because A is already known and we also know X, so just check whether there is a B satisfying A squared minus B squared equal to X. So just check whether A squared minus X is a perfect number or not. Okay, and we can check it in Owen. Or we can also use binary search and the complexity is log n. So if we use O(n), then the total complexity is just O(n). But if we use binary search, then the total complexity is n log n. If we check all of the divisor using the first solution or first idea, then the complexity is n square root n. And both of them is still accepted, but this one is faster. This is using brute force with this observation and then checking value a perfect square or not using O(n). How to use that? Just write this. let s is equal to square root a times a minus x. After that, just check whether s times s, and this is integer, s times s is equal to a squared minus x or not. Alright, if it is true, then a is valid, but if it is false, then just a minus minus. If a reaches 0, then just see out no, because there is no possible sequence. Alright, is there any question about the brute force tricks or brute force solution? Okay, so let's continue to the problem. This problem, given a sequence or an array A, and we want to create an array B. Okay, at first let's forget about array A. We want to create an array B that is satisfying this. P is all of the value in P is at least 2, and then all pair in P is coprime. All pair are coprime. Coprime means the greatest common divisor is equal to 1. Okay. Then what shall we do if we want to create any array D satisfying this condition? Just forget about, just ignore about the first condition. Okay. How to create an array and the size is up to 100,000, satisfying this. Then what is one of the example of valid P? Right. Do you know how to create one of the configuration? So coprime means both of them has different prime factor. Is it correct? If they has a common prime factor, then the greatest common divisor is not 1. But if the prime factor is different, then the greatest common divisor is exactly 1. That's why they are coprime. So how to make all of the value are coprime? Then just make all of the value are different prime numbers. So array B is 2, 3, 5, 7, 11, and so on. Okay, quite simple. All right, that is one of the good observation to solve this. Okay, you got it? Is there any question until this point? All right. Then what if there is another condition we have to satisfy, that P should be lexicographically greater than or equal to A. So we should care about array A. For example, for this case, okay, for this case, just make a minimum lexicographically P, and fortunately it is still greater than A, because the smallest prime number is 2, and then the next one is 3, 5, 7, and until this P is already greater than A. So just don't care about the next one. Just click 11. All right. But how about the second sample? Since the first value of A is 10, then we cannot use 2. We cannot use 2, we cannot use 3, 5, 7, but we can use 10. Since we want to find the smaller isographically P, we want to find the lexicographically minimal array but greater than or equal to 8. So just use 10 since we can use it. All right. As long as we can use this value, then just use it. Okay. After that, let's continue to the second index, because this is 3, and we can use 3 as well. And then after that 7, we can use 7 as well. Both of them are co-primes. All right. So the output is just same as the input. Okay. But if after 10 is 2, and then after that is 20, then what should we do? How do you think? What is the output if the input is like this? Okay, yes. Yes, then we use 3 since we cannot use 2 since 2 is already taken by 10. And then after that we can use 7. Why? Because we cannot use 5 since 5 is already taken by 10. All right. Okay. Yes. Not all prime. Okay. Then we can solve this. Again, we can use brute force as well, because 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 we can use like this. At first, the first value, just use this value, or let's create an array of Boolean. to check whether a value is true or not. We can use this or not. Okay, at first all of them is true except one. First one is n0 cannot taken, cannot chosen. And then for every input, for example input 10, then just use this if this is true. And then just factorize this, and for all prime number, for all each prime divisor of that value, all of the multiply is turned off. All the multiply of 2 and also all of the multiply of 5. Okay. After that, after we input the other value, if it is still true, then just use it. After that, just make all of the prime divisor is turned off. Okay. But when the value is false, we cannot take that anymore. Then we continue to the next step, which is we want to find the next true value. Just use brute force to find it. Just plus one by one until we get the true one. Okay. After that, because we already get the greatest or greater geography, so after that, just take from the smallest one by one. Take the prime number by one by one. For example, we take this and then just cancel off the multiply of this and then just continue, and then just cancel off the multiply of this and so on. All right. Put some numbers before. We will use brute force to find it only once. Correct? Okay. Let me see your questions. What if some number before this? Yes. So there are 3 steps. At first, just follow array A. Follow array A. But if already false, then let's continue to the second step, which is brute force. Brute force to find the next true value. After that, just brute force again. Brute force from the smallest. All right. Yes. So what is the complexity of the last brute force? The last brute force is just like we check for our prime number. So the complexity is same as shift and log n. And for this brute force, just on, even less than on. But okay, the worst case is still on, so just make it on. And then when we follow array A, we always canceling all of the prime divisor of that value, but don't worry, both of the prime divisor is different, because if there is a same prime divisor, then the value should be false. Then we continue to the next step. So since all of the prime divisor is different, then the complexity is just like sieve, just same as sieve. So generally the final complexity is sieve, and value of n is quite small, only 100,000, so we can use it. All right, is there any question about this problem? Okay, that is working. Okay, after that, let's back to the previous problem. So for this problem, we we don't use arithmetic operation but bitwise operation. So let's see. The input consists of some test case, and the number of test cases is at most 10,000. So hopefully we can solve one by one in O1 or O log n, because there is quite big. All right. So for each test case, given four values, that is L, R, I, K. What does it means? It means we want to find, okay, this is the problem. The main of the description is here. We want to find all integer x in range L and R such that x is not congruent to k in modulo 2 to the power of I. Okay. So L, R, K, and I already given. And I is only until 30. So we just need to check until 30 bit. And also K is no more than 2I. So the length of A no more than I. Okay, and L and R is up to 10 to the power of 18. So it is still can be stored in long log. Then how to find this? At first, we want to create a set or some set. This is a set of all value less than or equal to R. Of course, a value less than L is inside this. Okay. And we want to find this only. And also, we also need to create another set of a value that is less than or equal to R and X is congruent to K in modulo 2 to the power of I. Alright. So generally we want to find this one. Is it correct? Okay. Yes, okay. So generally we want to find all of the number of value less than or equal to R minus the number of value less than L minus the number of value that is not congruent. Let it be FR. FR means the number of integer no more than R that congruent with K. Minus this, and don't forget to include this, since this is removed twice and we want to make it neutral. So plus by FL minus 1. Okay. You got it about this formula? So now we just need to analyze how to find a function f. If we can find this, then just output this formula. Okay. So how to find a function f? So in order to find the function f, we analyze it in the form of binary number. So we want to find the number of integer less than or equal to R. That's the last bit, sum of the last bit is equal to K. All right. Then, okay, I think this problem is we don't want to find the number of integer, but the XOR of all integer. So my formula is incorrect. Not like this, but the prefix XOR of 1 until R and then prefix XOR of 1 until L minus F. F is the XOR of all number like that, and also F L minus 1. And this is not minus but XOR as well. Alright, this is the correct formula. Since we don't want to find the number of integers, but we want to find the XOR of these integers, of all valid integers. Do you remember how to find the XOR from 1 to R? I think I have ever explained to you how to find it. Is it correct? Yes, just use for conditions. Alright, so you don't want to explain this again. That's why in the solution there is a branching like this, a function to find the prefix XOR. Okay, so we already know how to find this and find this. And then how about F? So you want to find how to find fx. In order to find fx, you know, the last I bits should be equal to k. So all of the integer that ended with k is correct. So for example, 0, 0k, 1k, 2k, 3k, and also and so on. I mean like this 00k, 01k, 10k, 11k, and so on. Okay, is it understood? K means the bit of k. Alright. After that, because we want to find all of the integer that is less than or equal to r, then at first we want to check whether some last bit in r greater than or equal to k or not. Or let's make it x. Is the last bit of x is greater than or equal to k or not? If greater than or equal to k, then the number of integer is from 0 until x divided by 2 to the power of I. Is it correct? Equal to this. Okay. But if less than k, then equal to this minus 1. Alright. Is it understood? Yes, okay. After that, if this value is even, it means the XOR of all of them is 0 for this case. After that, for this case, we can just use prefix XOR from 0 until this value. Okay. But if this value is odd, then here is k. And we can use prefix XOR as well for the left side. Okay. Why? Because if this value is even, so k XOR k, 0, k XOR k, 0, and both of them have a match or a pair. So the result is 0. But if this value is odd, then one of them don't have any pair. So the result is 0 XOR k. The result is k. Alright. Can you implement this? Sometimes we need to try to implement bitwise operation more effectively. Or we can use in not necessarily the most effective one, but we can just check a bit one by one and then update a bit one by one. Okay. But I will try to show you how to implement it in effective way. Alright. At first, okay, I think we haven't submitted. This is the solution for problem cube. Let me remove this. The input is quite simple. I and then along LRK. Input LRK. And the output is prefix R XOR prefix until L minus 1 XOR prefix but F FR XOR F L minus 1. Okay. And then what is P prefix? We can use like this. If X and 3 is not equal to 0, then just return P X minus 1 XOR X. Else just return X. Return X. You know, if X is a multiply of 4, then the result is equal to X. Okay. If not multiply of 4, then just use prefix sum. Just use recursion X XOR with X minus 1. Okay. And then what is F? At first, we want to check whether X and 2 to the power of I think we shall create peak I, which peak I is equal to 2 to the power of I minus 1. And then if 2 and I is greater than or equal to K. Okay, and you know, we have to make a bracket here, because if we don't make a bracket, then the computer will check this first and then an operation is next, if I not wrong, if I remember correctly. If greater than or equal to K, then just forget it. But if less than, then we need to minus, or actually we want to minus I plus 1. Okay, because after that we want to shift-right it with I. That's why this line means minus after this. Alright. After that, just check whether X is even or odd. So if X is odd, Then what does it mean? It means the XOR of the last one is just 0. So just return the X shift left I. Else if X is even, it means the number of integer is odd. Then the XOR is K. So the return is this and then or J. Okay, it is correct. I'm not sure. Let's just check from the sample input. I think we also need to make a bracket here. Still different. So let's check from the P function. Okay, I think I input the from the different problem. So let me input the others. Alright, the output is just same. So hopefully it is accepted. So just check. Let me submit it. And how about the previous problem? I also got time limit. Maybe we need to do memorization for this, so we don't count the same value twice. Okay, yes, I will do that later. And for this problem, okay, finally accepted. Okay, for this implementation, do you understand all of the operation? Okay, that's great. This operation means we want to create a value like this 11111 with I bits. All right, and then for this, okay, for this means we want to check is the modulo 4 is not equal to 0. Okay, then return this, else return this. And then this case means we want to check the I last bit in X. So we ignore about the first one. We just want to see this. If less than K, then we want to reduce it in this bit. So if this value is equal to 100, for example, then become 99. Okay, we will reduce it here. After that, we will remove this, we'll delete this by shifting to the right, and then just check whether this is odd or even. If odd, since we include number 0, then the number of integer is even. That's why not added k. So the last bit is just 0. And bx means we want to do prefix sum for this value, but we will shift it to the left by I. Alright, so let's continue to the previous problem. Okay. For this problem, given an array A, and then we want to do some operations in order to make all of the value is equal. So if A is initially already equal, then the output is just 0. Or just one value, so it means it is already equal. That's why just do nothing, just do 0 operation. And sometimes we cannot do anything. We cannot do any moves in order to achieve all of the value is equal. For that case, just output -1. Okay. And the other case, just output the minimum number of operations to make all the value equal. All right. Then what is the operation we can use? So the operation is like this. Just take two value. Okay, sorry. Just take one value and then just split it become 2. We remove this and then add two values. But when we split, we add by k, split plus k. So the total of this value is x plus k. So just like we want to add this by k first and then split into two values. The sum of these values is equal to this. All right. Is it understood? So if k is equal to 0, it means if k is equal to 0, then we just need to split this become two values. Then what is the solution if k is equal to 0? Then in order to make all of them is equal, and we just can do split. For example, the value is 6 and 9. Then we can split 6 become 3 and 3, and 9 become 3 and 6, and 6 become 3 and 3. Finally, all of them are 3. Okay. So from an integer, because we want to make all of them is equal, then just split it into some equal integers. And the number of operation to split is the number of integer minus 1. Okay. So all of the value should be in the divisor of 9. Either 333 or 11111. Both of them is okay. But since we want to make it minimum, the number of minimum operation, and there is another integer, so we can make it 3. So we need to choose the greatest common divisor between all of the integers. If the greatest common divisor between all of the integers is 3, then just make all of them into 3's. If the greatest common divisor is 2, for example like this, then just make it 2. Okay, in order to make it minimum, so we want to find the greatest and common divisor because all of them can only divide it into its divisor. All right, so just find the greatest common divisor and then the answer is the total AI divided by greatest common divisor of all of them minus 1. Okay, this is the result if k is equal to 0. Then what if k is not 0? Then actually we can transform the array become like this. Become an array P, for example. Pi is equal to AI minus k. All right. So if we want to split AI become new AI, that the then satisfy this condition. So it means what if we convert into array P? So it means AX, you know, Pi plus K equal to AI. So AX equal to Pi plus K, and then, sorry, Px plus K, Py plus K equal to Pi plus K plus K. You know, there are two plus K's here, plus 2K's, and here also plus 2K. Then the equation become like this. Pi is equal to Px plus Py. It means its operation, we only split the value, just like if k equal to 0. So doing operation in A using this operation means we are doing an operation in B using the operation where k equal to 0. Okay, is it understood? All right. So just convert it into P, and then sometimes P can be negative, can be positive, can be negative, can be 0. Then what if there is a value of P that is equal to 0? If it is equal to 0, then it is cannot be split anything except become 0. Because if we want to split into a positive number, then there will be a negative number. So the value is different. So cannot be split except 0. That's why the other values will be 0 as well. So if there is a value 0, then the other will be 0. If all of the value is 0, then just do nothing. The output is 0. But if there is a 0, then and the other one not 0, then just see out minus 1. All right. If there is 0 and there is plus, then minus 1. If there is a 0 and then there is a minus, then just see out minus 1. All right. And then what if all of them is positive? Then just like what I have tell you before, equal to the sum of A divided by its common divisor minus 1. Okay. What if all of them are negative? You know, for its negative value, we can only split it into negative value. We cannot split it into positive, since if we split into positive, then the other will be negative. All right, so it means just use the greatest common divisor in minimum. So all of the negative value, let it become positive, and just use this value again. All right. And what if there is a positive and there is a negative? And so the output also -1. Why? Because negative can only split it into negative and positive can only split it into positive. And we cannot make all of them is equal. So if all of them is positive, there is a solution. If all of them is 0, there is a solution as well. And also if all of them is negative. But if it is hybrid between 0 positive or 0 negative or positive negative or both of them 0 positive negative, then the output is -1. Okay. Is there any question for this problem? So the key is to transform the array become G. Okay. After that, let's move to the previous problem. For this problem, the problem is quite simple. The input is only two integers, W and M. What does it mean? It means we have some we have scales. We have a scales, and we have some weighting loads with mass W to the power of 0, W to the power of 1, W to the power of 2, and so on. For example, if W is equal to 3, means we have mass 1, 3, 9, 27, 81, and so on. Actually, until 100 is so big, so we can assume until infinite, because we just need a small value, since M is also small. And then our target or our goal is to weight an atom with mass M. So if given an atom with mass M, can we make the scale balance? For example, if M is 10, then just put 9 and 1 here. Okay. And then what if the scale is 8? Can we do that? Then just put 9 here and put 1 here. And the scale is balanced. Okay. You got it? So what shall we do? So for its mass, we can put it to the left or to the right, or not use it. If not use it, it means multiply it by 0. If we use in the left, just multiply it by -1. If put it on the right, added by 1. All right. So it means for this problem, we just need to check, is there any array A satisfying this? A0 times W to the power of 0 plus A1 times W to the power of 1 plus A2 times W to the power of 2, and so on. Actually until 100, or just make it until infinite. That exactly equal to M. And W is at least 2. Okay. And array A only consists of an integer from -1 until 1. All right. At first, we want to increase the left side and the right side by this. Right. W to the power of 0, W to the power of 1, W to the power of 2, and so on. So it means A is only can be from 0 to 2. All right. Do you understand about this? All right. After we got this formula, just try to find this value. Actually, until W to the power of k less than m, since if it is greater than m, it is redundant. Or just until one mass greater than m. After that, just remove it. Or yes, just until m is okay, since greater than that always become positive, never become negative. All right. After we got this value, for example, the value is big M, then just try to convert this into base W. So if W is equal to 2, it means we will try to create a binary number, binary representation. So a binary representation always less than or equal to 2. So it is always yes. The result is always yes. And also for W is equal to 3, then both of the value will never exceed 3. That's why the output is always yes. But if greater than that, for example, W is 4 or greater than that, then sometimes the digit is more than 2. So in that case, just output no. But if all of the digit is no more than 2, just output yes. Okay. Is it understood? Alright, then let's move to the last problem. Actually, S and R is the same problem, but one of them is easy version and one of them is hard version, and the difference is only in the constraint. Then what is the question? So given some test case, but only 10, so don't worry. And then in each test case, given A, B, C, D, and we want to find the number of X and Y that X is between A and C. A is less than C. And then Y is inside B and D. And X times Y should be multiply of A times B. All right. Then what should we do to find the correct pair? In order to find the correct pair, if one of them is fixed, for example, we already fixed the value of x, for example, x a plus 1, then is there any valid y? In order to find the valid y, you know, y should be between p and d, and also xy should be is divisible by a times b. It means y should be multiply of okay, or yes, y should be multiply of a times b divided by greatest common divisor between a, b, and x. And the proof is quite easy, that y should be multiply of this. So in order to find a value multiplied by this, just find the value of this. So just check whether there is a multiply of z that is between p and d. In order to check that, just check whether g divided by z is greater by p or not. If greater by p, then there is a valid y. If less than or equal to p, then there is no valid y. Okay. After that, should we brute force the value of x from a to c? And the answer is no need to find a valid x, since the important key is in this value. Sometimes some different x achieve the same value for this. So just iterate for all greatest common divisor of a, b, and x. And you know, greatest common divisor of a, b, and x is always a divisor of a, b. So just factorize a and b, find all of the divisor of a and b, and then for that divisor, just check, is there any valid y for that value, and is there any valid x for that value. Greatest common divisor is equal to a specific value, means x should be a multiply of that value. Okay. All right. Okay. And no need to be co-prime, since if not co-prime, then it is better. So just check using this value as well, using this formula as well. Okay. With all possible z, divide a and b. And then how to find all of the divisor of a and b, since a times b is so big, until 10 to the power of 18. But don't worry, we have factorized a times b by this value, a times b. So just factorize a and then factorize b and then just combine it. All right. Yes, finally, we already discussed all of the problem. So good luck to solve all of them for your exercise in your long vacation. Okay. So thank you very much for this session and all of the previous session, and see you again in the next semester. And I hope to see you again in the better condition. All right. Thank you very much. Let's close our meeting with praying kafaratul majlis. Subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. That's all. Wassalamualaikum warahmatullahi Muhammadin. Alhamdulillahirabbil alamin. Wassalamualaikum warahmatullahi wabarakatuh. Yes, inshallah we meet again in